Hello everybody. On Monday we started going over section 7.2, or 7-2, estimating a population mean, and we talked a little bit about the t-distribution that we use. I passed out a t-table in class, and we talked about properties of the student t-distribution, and our main activity was building confidence intervals. So given sample data, taking a sample, computing, and in that sample, given a sample mean and sample standard deviation, what we do is we calculate, or we take the mean x bar, and then that would be our single best point estimate for the corresponding population mean in which we are estimating. However, every estimate is best, or let me say every estimate comes along with a certain amount of error. So rather than just using the sample mean as a single value estimate of the population mean, we construct what's called a confidence interval, which is a range of values for which the population mean could fall between with a certain level of confidence. And we can do any percent confidence for our confidence intervals. We can say do 90% confidence. We can do 95% confidence. The confidence level allows you to determine the t alpha over 2. And again, we'll do an example in just a minute. But the t alpha over 2 is always found from the given confidence level. And the other part of the formula for the error, so you find your t alpha over 2 and then you multiply it by the standard deviation divided by the square root of the sample size. Okay, so what I have boxed right now is I've got the sample mean, right here, x bar, and then over here in this formula, S is the sample standard deviation, and underneath the square root you have the sample size. Okay, so every one of these questions, they're going to give you sample data, they'll give you a sample size, usually coming from an SRS, or simple random sample. They'll give you the sample mean and the sample standard deviation, and then from the confidence level you would find the t alpha over 2. That comes from the confidence level. Okay, so we'll go ahead and go through the second example. We went through the first example yesterday. And remember the two required conditions where you technically need your sample to be a simple random sample. That means all samples have the same chance of being chosen, so you do your sampling in such a way that all samples of the same size have the same chance of being chosen. And the original population needs to be normally distributed, or the sample size needs to be greater than 30. Now we did this first example in class on Monday. And here is a second example. Let me increase the size of this slightly. Okay, so in this example, in a test of weight loss programs, a simple random sample of size 40 So you have a simple random sample of size 40, so that's going to be the sample size N. And then these 40 individuals use the Atkins weight loss program. After 12 months, their mean weight their mean weight loss was found to be 2.1. That's going to be the X bar. And it says that the standard deviation is 4.8. That's going to be your S. And it says construct a 90% confidence interval estimate of the mean weight loss for all subjects using the Atkins weight loss program. And then we'll answer the question, using the confidence interval, does the weight loss program appear to be effective and or practical? Okay. Okay, so the first part here says to check the required conditions. Since your simple random sample is of size 40, we're okay on the second condition. Our sample size is greater than 40. We don't know we don't know the distribution of weight loss for the population. We don't know if it's normal or not. So we need to make sure that our sample size is greater than 40. And I told you that it was a simple random sample, so there's a check there for the required conditions. Now, the T alpha over 2, we're going to get that from the table in just a moment. Okay, so you'd get out your T table from class, and what you would do is you would find the confidence level at the top. So we're trying to find we're doing a 90% confidence level. That would be in the first, second, third, fourth, fifth column at the top. Then we need to find the appropriate degrees of freedom. Now, the textbook, again, if you read the textbook, they give you, if your degrees of freedom, which in this case would be 39, the sample size is 40, so the degrees of freedom would be the sample size minus 1 of 39. And when you look down here, you'll see that in the table that I provided in class, there is no 39 degrees of freedom in the table. The T table in the textbook, I believe, does provide you with degrees of freedom 39. And the textbook tells you to do one of two things. If your degrees of freedom is between two degrees of freedom in the table, you can either choose the closer degrees of freedom, or you can be conservative and use the smaller degrees of freedom from the table. I think what I'll do is probably just go ahead and use the 40 degrees of freedom, because that's closer to 39. And if you look, this is in the 90%. I just boxed the 1.684. That's in the 90% confidence level column. So for this question, our T alpha over 2 is going to be 1.684. Okay, so T alpha over 2, using the table, I got 1.684. I chose to use the degrees of freedom in the table closer to 39, which was 40. Okay. And then you would calculate your error. So you'd take your 1.684 and multiply that by the standard deviation, which was 4.8, and divide it by the square root of the sample size, which was 40. And I think I'll just I'll be rounding my confidence interval estimates to 2 decimal places, so I think I will approximate my error to 4 decimal places to be safe on rounding. Okay, and then to 4 decimal places I get 1.2781. Okay, and then technically the units there are going to be pounds. Okay, so the units on your error are always the same as the units on your sample statistic. So in the case that since the mean here, the units on the mean are pounds, the units on the error would also be pounds. Okay. Well, next thing you're going to do is you're going to take your mean of 2.1 and add the error. So 2.1 plus the 1.2781, and I will round this to 2 decimal places. I will also take the mean and subtract the error of 1.2781. And my upper interval estimate, or upper interval limit, is 3.38 pounds, and the lower interval limit is 0.82 pounds. Okay, so what we've done is, with 90% confidence, we've estimated that the mean weight loss for the population of all people using the Atkins weight loss program, we estimated that the mean weight loss is between 0.82 pounds and 3.38 pounds. So the interval is, so I give the interval in two ways. So oftentimes you'll give your interval as an interval in interval notation. So it goes from 0.82 to 3.38. Or oftentimes you'll notice on the homework they want you to write the inequality, which I think is more instructive. Oh, excuse me, let me fix that. That should be 3.38 pounds. And right here, this mu in the middle, this is the population mean weight loss. Okay. So you've estimated with 90% confidence that the mean weight loss of all people using the Atkins diet is between 0.82 pounds and 3.38 pounds. So that brings me to the next part. When I interpret the confidence interval, we would say we are 90% confident the mean weight loss mu for all people on the Atkins diet is between 0.82 pounds and 3.38 pounds. Okay, so with 90% confidence, we estimate that the population mean weight loss for all people on the Atkins diet is between 0.82 pounds and 3.38 pounds. So the next piece then is using that confidence interval to determine if the weight loss program is effective and or practical. Okay, and what I would say is the weight loss program is effective. Okay, there was positive weight loss, right? Both of your confidence interval limits were positive, right? Which I would say this is basically saying the interval does not contain 0. Okay, so the interval does not contain 0. So I'm saying the weight loss program seems to be effective. Okay, but in terms of being practical, okay, remember this, if you go back and read the question, this weight loss program was tested over a period of 12 months. And if the mean weight loss is only between 0.82 pounds and 3.38 pounds over 12 months, remember, think back to practical significance back in Chapter 1. The mean weight loss is estimated to be so low that I would say that the weight loss program is not practical. The estimated weight loss is so low, the diet seems to be impractical. Okay. So there you go. There's another example of number one, computing or finding a confidence interval, interpreting that confidence interval with a sentence or a statement, and using your findings or using that confidence interval to make a qualitative assessment which is, yes, the weight loss program is effective, right? The interval does not contain 0. There was an estimated positive weight loss. However, over 12 months, with the weight loss being so low, the diet seems to be impractical. Okay, and then lastly, just like in section 7.1, if the sample size is missing, say you want to collect a sample and estimate a population mean, and you want to know what your sample size ought to be to make with a certain percentage confidence. You want to make sure that you're in error by no more than a certain value. So, assume we want to estimate the mean IQ score for a population of statistics students. Now, for these, you have to assume that you know the population's standard deviation. So if you know that IQ tests are designed so that the standard deviation is 15, how many statistics students must be randomly selected for IQ tests if you want to be 95% confident that your sample mean, okay, or your estimate of the population mean is within 3 IQ points of the true population mean? Now to do this, this formula is in the textbook. I did not give it in this handout. There is a formula for the error if you know the population standard deviation, and what that is the error in that case would be, so it's a very similar formula. It'd be z alpha over 2. If you know the population standard deviation, you use the z table to get your critical z value. And then you would multiply it by sigma, the population standard deviation, over the square root of n. And if you solve this formula for the sample size, n ends up being, let's see if I can get this right, this is going to end up being z alpha over 2 times sigma over the error, and the whole thing ends up being squared. In class on Thursday, I will be handing out a formula sheet. Again, this formula right here that I'm in a box. Most of the time we do not know the population standard deviation sigma. So this formula is actually not included in my formula sheet, but it is in the textbook if you do need it. Now for this problem, we want a 95% confidence level, and for 95% confidence we know that z alpha is 1.96. We would multiply that. We're assuming that the standard deviation of IQ scores is 15, and we want to be in error by no more than 3 IQ points. And let me compute this. And this ends up being 96.04. And remember that the rule for estimating sample size is that you always round this up to the next largest whole number. Okay, and forgive me, sometimes it's kind of hard to write with my pad pen. So to be within 3 IQ points of the true population mean, right, I want to make sure that my sample mean is within 3 IQ points of the population mean with 95% confidence. You would need to take a sample of 97 statistics students. Okay, so hopefully that helps. That should be enough to get you through the homework. Thank you for watching. Remember, the Chapter 7 worksheet is due on Thursday. I believe this homework is also due on Thursday. If anybody has any questions, we can go over them in class. Thank you for watching, and have a good Wednesday, everybody. Thank you.